So yeah, now for something a little bit different. As you said, I'm Patrick Clearwater from Swinburne University of Technology in Melbourne, Australia. And I'll be talking about Vulkan for gravitational waves, which is an astronomy topic. But I guess before I begin, I kind of wanted to say, like, I'm very new to Vulkan. I think 12 months ago, I'd heard of Vulkan maybe, but may have also thought it was just a Roman god. And sort of 6 or 8 months ago, I started doing this experiment that I'll describe, and it's been a really fun thing to do. So who am I? Astrophysicist by training. You can also say astronomer to impress people, and software developer if I want to sound like I earn money. So my academic background is a PhD focused on gravitational wave data analysis. And as that name suggests, it's a pretty computationally heavy topic, which is good because I also really like computers. So astronomy is great. I strongly encourage you to do some. But I ended up in a group called Astronomy Data and Computing Services, or ADAC for short, which is based at 3 universities in Australia. So Swinburne, where I am in Melbourne, down in the southeast, Curtin University over in the west, and Macquarie University in Sydney, and we don't like Sydney very much. And so ADAC is funded by the Australian government to provide software support to the Australian astronomy community. So in some sense, we're a software engineering, software development consultancy that you can access if you're an Australian astronomer. So we do lots of things. One thing we do is stuff like software best practices and automated testing. And we've almost got everyone in the community to use version control for their codes. There are still a few holdouts, and automated testing will be maybe the next thing that we push on people. But we also can do stuff on training and documentation. We did a few projects that were taking astronomy codes and making them web accessible, which turned out to be extremely popular. We've done some user experience research, and we also do optimization of existing codes, which hopefully encourages you to think I haven't ended up in the wrong conference. And so that optimization can include things like if you swap the order of these 2 loops, it won't take 6 days on a supercomputer, but it will take 60 seconds on your laptop. Sometimes it's rewriting things or doing algorithmic research. But one area that's been really big over the past 5-10 years has been identifying algorithms that are extremely parallel or can be bullied into being extremely parallel and running them on GPUs. And just to finish the advertisement for my employer, we support university research translation efforts, and we operate 2 research supercomputing clusters, which are free for the Australian astronomy community. And as I'll sort of get to, they have NVIDIA, both of them have many NVIDIA GPUs, but maybe not forever. And as a model, it's kind of like a little bit out there and interesting because my team is maybe 50% people with an astronomy background and 50% people who are computer scientists or data scientists and not from that astronomy background, but it's really been taken up in the astronomy community, and there's this idea of potentially expanding it beyond astronomy, but I guess we'll see how that goes. And of course, because it's free for astronomers to use, it's government funded, which is always a challenging thing in democracies. So some people may be sitting there thinking, astronomy, you stay up really late and look through telescopes and make observations of Saturn or whatever. And that certainly does happen, but modern astronomy is an extremely data and compute intensive discipline. So I've kind of got an illustrative example there, which is the square kilometre array, which is so actually 3 telescopes split between Australia and South Africa. And it's called the Square Kilometre Array because it will have a sort of square kilometre of collecting area. I don't think they'll end up getting there, but even at a smaller scale, like the data transfer rates and processing needs are pretty intense. So it's not quite as bad as that because, of course, you can do some of the processing closer to where you're getting the data, but like it's cutting edge stuff, and anything that the community can use to, like anything like GPUs or whatever that make things faster, translate into really good scientific outcomes. So yeah, obviously GPUs are of significant interest. They've been reasonably widely used in astronomy for a while. So I found 2 papers there, sort of 2010, 2011. So in some ways, the discipline was a bit of an early adopter. But I think the flip side is there's not all that many people in astronomy who are interested in GPUs for GPU's sake. It's very much a practical use. The idea is to use the GPUs to do a thing. So this is my most controversial slide. So if anyone wants to throw Rotten Tomatoes at me or anything, now's the time. And I put this slide in to be a bit provocative, but certainly in Australia, this has been my experience. People who are doing sort of low-level GPU stuff, they use CUDA. Obviously, some people are doing stuff with higher-level frameworks like PyTorch. But if you want something at the CUDA level, you use CUDA. And in some ways, that's a fair enough thing. Like NVIDIA has put a lot of effort into CUDA. It's quite a good platform. They're responsive to these sorts of use cases, but it does raise some questions. So I kind of put some angry looking things there, but like the vendor lock-in, I think is a reasonably big one. As I said, our two current supercomputers both have NVIDIA chips, but they're quite expensive, and like it's a money constrained discipline. And sometimes you just want options. And if we're doing open science, maybe we should be using open standards. I say that a lot. No one else in the community really cares too much. But I think the big thing that I put in that less scary box is, was this a decision that the community made, or is it just the default we kind of ended up in? And I think it's very much the default we ended up in. CUDA was there, and once your supervisor used CUDA, or the supervisor students use CUDA, and it kind of suffuses into the community. And one of the great things about where I work is we have a bit of leadership in the sorts of technologies that are used. So it's a place where things like, say, Vulkan could be considered. So I asked what alternatives exist. And essentially the question in my talk is, could we use Vulkan compute shaders to sort of do the same thing that is currently done with CUDA? So I decided on CUDA fairly early on because I was, I wanted to pick something, and my goal here was not to do like a wide survey of alternatives. It was just to try one thing. And so my thinking was to put a relatively simple but real search code to Vulkan and see what happens. So this section of the talk, it won't be on the exam. This is a primer of what we're going to do with Vulkan. But I've got to say, ultimately, what I'm going to say next is much easier than understanding human perception of colors. So, So anyway, I said, what are gravitational waves? And this section of the talk, I've got to say, has some lies and simplifications in it. So gravitational waves are predicted by general relativity. General relativity, as I'm sure you all know, treats space-time as this sort of geometric object which can be deformed by matter and energy. There's a nice demo there. You've got your star or your planet analog, and you roll something, and it follows this curved geometric path rather than going what you might think of as a straight line. And that is a description, and indeed the modern description of how gravity works. So gravitational waves, and again there are some simplifications on this slide, occur when an accelerating mass causes a wave to travel through this space-time geometric object. So you can sort of think of it like a pebble dropped in a pond. You get these waves coming out. So roughly speaking, any accelerating mass will cause a wave, will cause a gravitational wave. So I can get some gravitational waves by waving my pointer at you. But in practice, the gravitational waves would be so unbelievably small, they would not possibly be detectable, which is why gravitational waves are an astronomy concept, because astronomy is where you get the big, dense things moving really fast and possibly producing something. So how do we detect them? I'm legally obliged in these talks to mention our space-based interferometer projects that are ongoing and the pulsar timing projects that are ongoing. But of particular interest to me is the so-called International Gravitational Wave Observatory Network, which is a network of terrestrial interferometers. So there are two of them, called LIGO for, I guess we're not very good at naming things. And so the principle of operation for these sorts of detectors is you see those long arms. So you shoot a laser down that way, bounces off a mirror and comes back. At the same time, you have the laser going that way, bounces off the mirror and comes back. And you use the interference of the returning lasers to measure the distance in length of your two arms. And when a gravitational wave passes through, one arm will get slightly longer, the other arm will get slightly shorter, and you hope you can detect that and learn something about space. So those tunnels are 4 kilometers long. The change in length that we are looking for is 1/1000th of a proton diameter. So I'm not exaggerating too much when I say these are amongst the most sensitive scientific instruments that we have. So these two detectors are in the United States. So one in Louisiana down southeast, one Hanford, Washington, northwest. There's also Virgo in Italy, and which is based on the same principle, and Kagra in Japan, which is the same principle, but they put it underground and made it really cool, which, as in low temperature, cryogenically, and that has certain theoretical advantages, but I think they found the going quite tough from an engineering perspective there. So even in the UK, I did a little bit of research. The University of Glasgow has a 10-meter interferometer, which is used for sort of prototyping and developing new technology and training. It's too short for astrophysical detections, but it's cool to know that they're kind of everywhere. So anyway, I've told you these lies about proton diameters and whatnot, but you might be asking, are they even real? And so I contend yes, and in 2015, we made a detection of 2 black holes merging, which has that very, very nice name, GW 150914. And I won't sort of explain this plot in great detail, but you can see the 2 detectors that were operating, and you overlay one on top of the other, and it looks about the same, and they're quite far apart. So it's unlikely to be noise. The second panel is a numerical model. It's a good fit, and there's a sort of pretty picture down the bottom. But all I've done is shown you a slide and a plot, and you can prove anything with statistics and plots and so forth. Are these? You might still ask, are these real? So, and I should also say on this, the time scale is sort of half a second or so, because it's only at the very moment where the 2 black holes merge that they produce waves that have the right frequency and are sort of strong enough to be seen. So this is a detection of a neutron star merger, which also has a nice name. And here you see the time scale's a bit longer because it's slower and still detectable. So the gravitational wave data are on the left, and it just looks like this strange streak that you can maybe trust me or not. But in this case, there was a reason to expect there would be an optical counterpart. So the top right picture is a Hubble Space Telescope image that was taken a few months before this event. Hours after the event, they started looking in the predicted location for it, and you can kind of see a new transient object has appeared. It's called a kilonova, which is, I guess, brighter than a nova, but not as bright as a supernova. So that's kind of cool. We would have had to have really bribed people to fake this up. And so in total, about 150 of these compact binary coalescences have been detected. So for this code, we're going to forget all of the stuff that we've found and search for something we haven't found yet. So the code I'll be describing is a search code for continuous gravitational waves from neutron stars that are in these objects called low mass X-ray binaries. Neutron stars are very interesting objects that I can talk to you about for a long time, but for your purposes, just imagine them as very dense objects that spin quite fast. So they maybe weigh as much as the sun and are sort of 10 kilometers across. So, smaller than, well, maybe same size as Cambridge. And the spin frequencies can be up to the hundreds of hertz. So it's quite an extreme object. And the X-ray binary comes from this artist's impression where you see a so-called main sequence star, a normal star that's accreting onto the neutron star, and it causes X-ray emissions and, you hope, causes gravitational wave emissions. And so continuous gravitational waves are a bit different from the compact binary coalescences. The CBCs are very short. They lasted seconds to tens of seconds, whereas continuous waves, as the name suggests, are present in the data all the time, but are much, much weaker. So it's a real data analysis task. So you'll see that the the red border has disappeared. So this is examinable again. For our purposes, this code does three things. So they built the detectors on the Earth, which is good for maintenance, but it does mean that they move with time because the Earth rotates every 24 hours and goes around the sun every 365 days. So the thing you're looking for, it'll experience a Doppler shift from that. Similarly, because the source is in a binary. Oh yeah, but the Earth's motion, you know where the Earth is. The people at NASA have sorted that out for us. You also need to account for the binary star motion. And that's a little bit harder because you can look at it and measure it, but the measurements are a little bit vague. And so you need to do some real searches there. You've only got error bars. And finally, as I said, these objects, they rotate quite fast, and normally it's a very monochromatic frequency. So the frequency doesn't change very much, but there's good theoretical reasons to believe it changes just a little bit. So it's not quite as simple as doing a Fourier transform on all your data and looking at the peak. You have to kind of be a bit smart. And we came up with a very, very smart technique beyond the scope of this talk for doing that. So there's the paper that describes the algorithm and being used by people to do searches. Some of those people have been me, but some of them have been other people. And the code that was used for that search was the CUDA code. So for the purpose of my experiment, accounting for the Earth's motion, that now has a CUDA version, but it's annoying to port for Vulkan for what I'll call ecosystem reasons. But the other two are both very, very sensible candidates to trial a Vulkan port of. So the Vulkan version, well, we'll use Vulkan compute shaders, of course. For style points, we'll write it in Rust and write the shaders in Slang. And you know, if you're doing something like this, why not do the most complicated thing you can possibly do? And so I did that, and it produced the right answers, which was good, but hopefully not too surprising. It was somewhat slower, and I'll talk about that in a second. And certainly, and this is where my newness to Vulkan comes in, there was a lot more typing than the CUDA version. So lessons that I took from it. As I said, there was a lot of typing. So the top is the Rust and the Vulkan, and it's, you know, you keep typing all that, and your fingers slowly wear themselves down. Whereas the CUDA version is sort of called CUDA malloc, and so that's bad. Scientists don't like typing too much, but of course the boilerplate is my fault. Like I intentionally for this experiment very much wanted to just do it in Vulkan. But obviously, and you know, not using something like VK Bootstrap, which I learned about it at this conference. And you know, none of this typing is sort of fundamental to the problem, particularly if you know you're willing to give someone the easy version that they need. Like certainly, if you're using compute shaders, there's a whole lot of graphic stuff you just don't need to worry about that I'm very pleased about. But I think it would be sensible to develop a framework or a library for this. Maybe extending an existing one, maybe just finding a good one, or maybe something that's astronomy specific. I think that's an open question and something to think about. And of course, I did it in Rust, but like we've been totally unsuccessful at getting astronomers to adopt Rust, so it'll have to be done in C++. But anyway, these things happen. So the accuracy and the performance were fine, which I don't think comes as too much of a surprise because the code is actually not that complex and it's running on the same hardware. One of in some ways, the computational meat of this code is a fast Fourier transform. And in CUDA, of course, a lot of time and effort and extremely smart people have been spent on making very fast CUDA, very fast Fourier transforms. So I think, you know, some attention would be needed there to supply those sorts of primitives so people can just pick them up and use them. And then the third lesson, which is sort of maybe a bit more depressing, is there's a need to develop a real use case for this. So it was very fun for me to do, but real astronomers need to get real astronomy done. If CUDA works, I think it will be difficult to convince people, you know, you should throw away all of your knowledge and develop some new knowledge for some, you know, open standards or vendor lock-in related reasons. But I think that this is a problem that can be addressed by just developing it and being ready for when the time is right in the ecosystem. And in particular, we've got supercomputers. Our new supercomputer came online in 2023. We'll need a new one in a few more years. And if it's not using NVIDIA cards, the world may be a little bit different. So yeah, I think it's quite important to watch for that. So the next steps. I did this for fun, I say on my own time, but actually my boss let me do it and paid me to do it and all that sort of stuff. So thanks to him and Swinburne for letting me waste some Australian government money on it. So I think it'd be worth developing this into a more serious piece of code and convince people to run it on different systems, and maybe even, the continuous gravitational wave searches is great because we haven't detected anything. So armies of PhD students are thrown into the breach of searching for different types of things in different data. So one of them will be hopefully silly enough to use the Vulkan code rather than the CUDA code for this. And finally, I think it's important to go to conferences to tell people how cool astronomy is. So I hope that I've achieved that with this talk. So in summary, CUDA, very commonly used in astronomy to drive GPUs. It would be nice to use Vulkan compute shaders for that. And this works. Thank you very much.
Thanks for the talk. It was very interesting. I have a question that's got nothing to do with Vulkan, but I am very curious. Obviously, you're picking out very small signals in a lot of noise. So just from an anecdotal perspective, like how much noise is generated by sunlight shining on one arm and not the other, a truck driving by, somebody sneezing in the next town over, like how much noise are you dealing with?
A lot. So the mirrors that the lasers bounce off on are suspended on these 4-stage, I guess, pendulums, but pendulums designed to cancel each other out. But yeah, a lot of effort is put into that. So one very amusing anecdote is one of the sites, they had this sort of not quite 1 hertz noise line that they saw, and it was quite reliable. But there was variance, and they thought, and it only happened on hot days, and they thought this is probably the heating system, because it's something in it's coming on once a second, and it's not perfect. These heating systems, very high currents, they're not really precision instruments. So they did some research, couldn't find it in the heating and cooling system, but then someone went outside and saw the cooling pipes outside got this layer of ice on it, and woodpeckers would come along and peck on. But yeah, no, the noise isolation is an extremely hard problem. For continuous waves, it's less of a problem because you're taking so much data. Someone sneezing, it gets washed out in the noise. But certainly for the compact binary coalescences, it's really important. So where is it? On this one in LIGO Livingston, it looks like a very, very beautiful and sort of noise-free thing, but there was actually a detected glitch right about there, and they managed to model it and remove it. But it was very unfortunate that the very first one of these that we saw was affected by quite a significant noise glitch. But yeah, no, it's a good question, and there are conferences devoted to answering it.
Mm-hmm.
So you chose 2 of the 3 libraries initially to convert to Vulkan. Where is Vulkan missing that you couldn't convert the first one that was in CUDA?
Well, ecosystem reasons means that I didn't understand that part well enough to be totally confident on it. But actually, the other reason is that particular bit of the code is something that's buried deep in a library that is it's a sort of thing, it takes you about a week to compile for the first time to figure out all the dependencies. So I don't think there's anything that would make it impossible to do, but I worked with the guy who did the CUDA version, and he spent significantly longer getting CUDA integrated into it than he spent writing the CUDA code to do it. So I didn't want to kind of tackle that challenge. Whereas the other 2, I wrote the original CUDA version, so I kind of knew my way around, and I knew I could pull them out pretty easily if I had to.
So a comment and a question. First of all, I am really excited to see this because one of the things that I have been thinking about a lot over the last couple of years is how can we start addressing the needs of the scientific community with open standards? We have OpenCL, but it's got a lot of problems. And if Vulkan is able to maybe address some of those and get something that's a little bit closer to what we want, I'm happy to see anybody even trying it out, because I do think that this is something that Konos should be looking at, and it's something that I personally would like to look at in the next few years. So very excited to see your talk. Now the question, where's the code? Is this something that I can pull and use as a benchmark and throw at my driver and see how the shader generation is and try to make it faster?
There will be code in a couple of weeks, but sometimes when we write abstracts, we're a little bit aspirational. And I had a very busy last 6 months of last year, so I may have got it to work on the plane on the way over. So I'd like to clean it up just a little bit. Yeah.
That's understandable. But I'm like, anytime we can get interesting, different workloads that we can throw at our drivers and try to optimize, it's good data for
Yeah.
the
That'd-
Vulkan ecosystem.
That'd be great. And like one thing I've found doing not just this thing, but other CUDA things is the problems that you need to solve are a bit different from graphics. Like latency is not usually so important. Don't need to hit 16 millisecond frames, but throughput is very important. And I'm assuming that will push the drivers in different ways. So yeah, I'll when I've got a version on GitHub, I'll send it to you.
I'd appreciate that. Thank you.
Great talk. You are using Slang. What other shading languages or options did you evaluate, and why did you settle on Slang? And does Slang is Slang fully satisfying, or is there other things you would like to see?
So I didn't do a particularly comprehensive evaluation, I have to say. I picked Slang because it seemed to be the new hotness that everyone is chasing. And I sort of did some early stuff in GLSL because I guess that's the default, so to speak.
I can see why you wouldn't stick to that.
Sorry?
I can see why you wouldn't use that.
Yeah. I mean, I think it is something worth doing. And in much the same way, like we should be investigating non-Vulkan things for this as well. But I kind of very intentionally chose to say, I'm going to have a highly opinionated path and just pick these things, even if, even if those opinions are not based on any sort of science or evaluation.
So in your own words, this is more of a default than a decision.
Exactly. But only because you guys all say how good Slang is.
I can shut the break.
Over here to your right. So I'm curious because when I think of a scientific workload, and this might be maybe naive, I just assume it's like you load the data on once and it's just a large big kernel. So I guess how much of the code is Vulkan runtime, managing memory versus just shader code? So is this a Vulkan problem or a CUDA shading language problem?
So this particular one, it has to be said, is probably closer to the shading language problem. I didn't do any super complicated Vulkan stuff. It was closer to load the memory in, run the shader. But workloads do differ. This is quite a nice problem because once you've loaded all the stuff in, you just kind of tell the GPU to push really hard on it. But there are different problems that I think rely on it's too much data to load into memory at once, so you need to do something fancy and stream it in. But I would say this is one of the simpler use cases from a Vulkan perspective.
So I guess maybe my question would have been if there was a magical, today CUDA could compile perfectly the Spear V and that was not the problem. Is it the Vulkan that's the problem, or do you think it's also just having the whole ecosystem, the tooling, or where do you think the problem lies that makes it hard to adopt?
Well, I just think people won't adopt it. But I the ecosystem is very important, right? Because people don't want to write their own FFTs. They don't want to write their own matrix multipliers or whatever. But yeah, I actually don't think that there's any good reason people couldn't adopt this. People will just do what they did before. So yeah, showing that it is possible, I think, was the objective of this experiment, basically.
Question over here. Time for one more. Yeah.
All right. So I'm gonna ask a very quick question, which I think you're gonna give a very quick answer to. So what about OpenCL, SYCL, this weird thing from AMD that compiles CUDA?
Yeah, exactly
hit.
the same. Yeah, it's exactly the same sort of answer. Like I picked Vulkan because I wanted it to be a finite problem. I was also very conscious that if I do too much research, I'll get hoodwinked into sitting on a committee that has to decide technologies for future use, and I wanted to avoid doing that.
Okay, I get that. And what resources did you use for learning Vulkan? As you said, you were new. Like any of the last year's conference talks or blogs or anything like that?
I'm very bad at watching talks. So I didn't use any of last year's talks, but that's not a reflection on their quality. Look, mostly talking to Kane, who I know and who bullied me into doing this, but also like just searching the internet. How do I do thing Vulkan? And I usually found pretty good resources. I should read the spec more, but specs are hard to read. Just sort of general searching on the internet.
Time for two more questions, I think. Do you want to go?
Yeah. So earlier in the conference, we saw Slang PY, and I think that solves some of the like Vulkan setup stuff that you talked about. Do you think that is something that would be valuable to the scientific computing community?
Absolutely. So to my chagrin, Python is extremely popular in astronomy. I have some aesthetic objections to it, but like it's a good language. It solves a lot of problems, and like a lot of astronomy codes are written in Python. Again, because this was my experiment, I didn't sort of look into that sort of stuff because I wanted to avoid writing any Python. But I certainly think that like a more integrated strategy would use stuff like that. Yeah, definitely.
So I assume you're using solely Slang's Vulkan SPIR-V target. Did you have any opportunity to compare Slang CUDA output to the original handwritten CUDA, or try out, Slang CUDA versus Slang Vulkan?
So until I saw your talk, I didn't realize Slang could do that. But now that I know, like I am so keen to find out. So yeah, that was very useful.
So we're going to squeeze one more question in.
I'll make it quick. Is GW 170817 just 2017, August the 17th?
Exactly.
Yeah.
And so the scheme is thought out, right? But whether it's truly thought out in an age where we're detecting multiple things a day, we'll see. It might become 170817 AEF or something.
And on that last question, I'd like to thank our speaker again. Thanks very much, everyone.